Okay, so in the last few videos, we were talking about implicit differentiation and this idea of can you find the derivative of a function if you don't actually know what the function is? And apparently, as it turns out, we can because we actually did several examples of it using this implicit differentiation trick. Now we want to see why that's actually useful by looking at another class of functions that are differentiable and maybe figure out how to find their derivatives. So, suppose we have this. Y equals sine inverse of x. The inverse functions, you all know there's inverse trigonometric functions. You did them all in trig. I'm not sure how much time you spent on the graphs in 172. They're in your book. They're in your trig book. They are definitely differentiable. And if they're differentiable, they're nice and smooth curves and all of that. They're continuous. If they're differentiable, then of course what we care about is how do we find the derivative? And as of right now, that's not a polynomial. It's a trig function, but it's an inverse trig function. So what we know about trig function doesn't really help us. How in the world do we actually find that? But we can actually use a trick that you used in 172. If I want to solve this, I don't like the inverse, so I'm going to get rid of it. I'm going to take the sine of both sides. Then I get sine y equals sine inverse, which we know cancels, x. And now, just keep in mind, our ultimate goal here is to find y prime, dy dx. Well, now I've rewritten the problem. Now I'm going to take the derivative of that. I know now that I can take the derivative of sine y using my implicit differentiation. So if I do that, the derivative of sine is cosine. The inside function y stays the same. Then I take the derivative of y, which is y prime. That's my chain rule. And this is equal to the derivative of x, which is 1. Now, since my ultimate goal is to find y prime, just isolate it. Divide cosine y. And I get y prime equals 1 all over cosine y. And now, question is, that's definitely y prime right there. But y prime is written in terms of the function y, which I don't really know. I guess I could substitute y equals sine inverse of x. But then I'd have y prime equals 1 all over the cosine of the sine inverse of x. And if you remember 172, that's really kind of awful. And I don't want to do that. So I'm going to do something else. That again comes from the 172 you remember. There's all those identities that we told you in 172 to memorize. The first one, the most basic one, is the Pythagorean. Sine squared of x plus cosine squared of x equals 1. In this case, this is in terms of x, but I'm going to change them to y's just because that's in terms of y. It doesn't change the identity. So now I have this Pythagorean identity. I'm going to solve it for cosine y. So subtract the sine squared. I get cosine squared y equals 1 minus sine squared y. Now I'm going to square root both sides. And I get cosine y equals the square root of 1 minus sine squared. And here, I'm aware there's two values here when you square root the square, but we're only going to take the positive one. Don't worry about that. And we get cosine y equals the square root of 1 minus sine squared y. Well, now rewrite that. So I get y prime equals 1 over cosine y, which is the square root of 1 minus sine squared y. Which doesn't appear to have actually helped me. I mean, I didn't like having this derivative in terms of the implicit function y, and I still have it in terms of the implicit function y. But now, I actually know what sine of y is. It's x. So up here, if that's sine y, maybe I'll draw it right over here too. Square both sides. And I get sine squared y equals x squared. Now I can do a direct substitution. And I get y prime equals 1 over the square root of 1 minus sine squared y, which is x squared. And now there's my derivative. If this is sine inverse of x, that's the derivative of sine inverse of x. And one thing I will point out, we're going to maybe do a few more examples of this. This trick will work for all 6 inverse trig functions. Just like we had tricks to find the derivatives of the 6 trig functions, you can do these same type of algebraic tricks to get the derivatives for all 6 inverse trig functions. I'm not going to do all of them just because that would take too long. I wouldn't even do them if we were in a seated class. I would encourage you to work through them yourself just as a way to practice this algebra and kind of get an understanding of it. But there is, did I write the page number down? Page 66 in your book actually lists the table. Just like there's a table for the 6 trig functions and their derivatives, there's a table for the 6 inverse trig functions and their derivatives. But let's see. We can expand on this because we said repeatedly that's pretty much what we do. Once we have a basic idea of how to get a derivative, then we try to make it more complex. So I will leave that here just so we have the derivative written out. But suppose my function is y equals sine inverse of x squared plus x. That's now a composition of functions. It's the sine inverse function and this function on the inside. So do not try to make it more complex than it is. It's a chain rule. We say y prime is equal to outside function. The sine inverse function is the outside function. It's that right there. It's 1 over the square root of 1 minus x squared. But keep in mind, this x squared, this x, is actually from our original sine inverse of x. My x on the inside has now been replaced with this function. So when I take my derivative, I replace the x with what's on the inside, x squared plus x squared. Now, chain rule says I multiply by the derivative of the inside, which is just 2x plus 1. And now there's my derivative. And again, we don't need to overcomplicate it. Derivative of the inverse function. But since this on the inside changed, this changes. I replace x with whatever's on the inside. Then I take the derivative of the inside, because that's what the chain rule says to do. So we'll do maybe one more of these with a different trig function. So in my notes I had, let's see, arctan. Y equals arctan of x. I want to find y prime, so I take the tangent of both sides. And I get tan y equals tan arctan cancels x. I take the derivative. Implicit differentiation, the derivative of tangent is secant squared of y. Then I do y prime equals the derivative of x, which is 1. Now I get y prime equals 1 all over secant squared y. And now I know how this is going to work. Ultimately, I'm going to want to write this in terms of tan y. So first I'm going to apply a Pythagorean identity. If you remember all of your Pythagorean identities, there's the basic one, sine squared plus cosine squared equals 1. And then, if you divide everything, let's see, I want secant, which is 1 over cosine. So divide everything by cosine squared. You should have these memorized, but on the off chance you're not sure, I'm being nice and doing this again. I don't have room for the cosine squared there. There we go. Sine squared over cosine squared is tan squared y, plus cosine squared over cosine squared is 1, equals 1 over cosine squared, which is secant squared y. Now, secant squared is equal to tan squared plus 1. I don't need to rewrite that, it's already right there. So now I can rewrite this as y prime equals 1 over tan squared y plus 1. And now, well, up here, tan y equals x. I need a tan squared, so I square both sides. And I get tan squared y equals x squared. Now I can do a substitution. And I get y prime equals 1 over x squared plus 1. And now I have the derivative for arctan. And of course, we can then expand on this. If we have y equals tan inverse of 2x cubed plus 6, well then y prime will be 1 over x, which is the inside, so 2x cubed plus 6 squared plus 1 times chain rule the derivative of the inside, which is 6x squared. And there we go. That's 2 of the inverse trig functions. Like I said, all 6 of them are listed on that table on page 66 in your book. Learn them. It is useful to learn them. And to a certain extent, we had the inverse for sine and the inverse for tangent now. And we notice there's a similarity between them. There's kind of patterns you see. And if you study them and work with them a little bit, it makes it easier for you to be able to look at this and say, oh yeah, that looks like the right answer. 1 over x squared plus 1. That's just a chain rule going on. Because there's a pattern to how these inverses of the arc trig functions works. But I did 2 of them. I would encourage you, if this was a seated class, I would have you kind of break up into groups and do them. Do the other 4. See if you can work through the algebra. If you have trouble doing it, feel free to just call, email, text me or whatever, and maybe I'll make another video kind of solving some of those out.